Hello, AP students. This is our second podcast on solutions. And in this podcast, we'll talk about solution formation and the energy that is associated with that and the factors that affect solubility. Okay, so let's start out with the idea of solvation or hydration, as it's called if the solvent is water. Okay, and so how does the liquid solution form? Well, you have to separate the solute from itself. You have to separate the solvent from itself, and then you have to allow the solute and solvent to intermingle and mix. So let's look at this in a picture form. Okay. Okay, so here we have the solute, okay, and then it has to be separated, so intermolecular forces need to be overcome here. Here we have our solvent, needs to be separated, and then the solute and solvent need to be allowed to be mixed to create the solution. And so each one of these steps requires either energy to be put into it or energy to come out of it. And so when you add up the energies associated with each step, then you get your overall delta H for the solution. Okay, so the first steps, 1 and 2, where you're separating solute and solvent, those require energy, so that's an endothermic process. And then when the solute and solvent are allowed to mix, that's usually an exothermic process, and energy is released due to more stability. Okay, so adding the steps delta H's together gives you the overall delta H for the solution, and it could be positive or it could be negative. And positive delta H's, of course, show instability or a raise in enthalpy, and so those solutions tend not to form, where negative delta H's show a greater stability, the lowering of enthalpy, and those solutions tend to form. They tend to mix. Okay, so here you're looking at some enthalpy diagrams of both an exothermic, so a lower delta H, and endothermic, a higher delta H. So this is, again, just another visual of the energies of solution formation. Okay. Okay, so here's a good question. Can you explain why why oil and water don't mix? Okay, so try and talk about it in terms um, of the delta H involved. Okay, so as we look at this, we see that oil is a long-chain hydrocarbon. Okay, and so it is nonpolar, which means it has LDFs, right? The London dispersion forces for intermolecular forces. Okay, and LDFs depend on the molecular size. So the longer the chain, the greater that London dispersion force. Okay, so that delta H1 is going to be large. Okay, and then delta H2, that's where we're separating the water molecules. That depends on overcoming hydrogen bonding, and that again is going to be large. Okay, and then your delta H3, where they are allowed to mix because their intermolecular forces are different, the delta H3 will be small. Okay, and so overall, the delta H of the solution will be large and positive. And so therefore, instability, an increase in entropy, and so therefore they don't mix. Okay? All right, so here's a general overall table for you to see what's gonna form a solution and what won't. And so just kind of remember likes dissolve likes, and then that helps you to know or to know what's going to form and what's not going to form. But they give you the outcomes. Okay? All right, so in general, where will we see solution formation? Well, the factor that's going to favor that solution formation is if we have an increase in what's called entropy, where the solute and solvent are more chaotic, more random. They can mix easier. Okay, processes that require a large amount of energy tend not to occur, especially if that last step where they're mixing is small. Okay, so just remember, likes dissolves likes. All right, so what's going to affect solubility, the ability of a solute to be dissolved in a solvent? Well, the structure, okay, remember likes dissolves likes, so whether it's polar or not, okay. If it's a gas, the pressure of the gas above the solution will affect that, and that's called Henry's law. We'll look at that in a minute. And then, of course, temperatures. Temperatures affect solutions differently if the solute is solid versus the solute being gas. Okay, so here is the Henry's law, and basically it's just saying that the amount of gas that you try and dissolve into the solution is directly proportional to the pressure of the gas above it. So kind of like when soda pop is being bottled, that's why they put the CO2 on top of the 2-liter bottle so that the gas, the CO2 stays inside the solution. And then when you open the cap, of course, you're releasing that pressure that's been bottled inside, and then your solute comes out and your soda gets flat. Okay, so here's just a visual of what's taking place. As you increase the pressure from A to B here, more of the gas solute will dissolve into the solution till we reach an equilibrium where the gas going in is equal to the gas coming out. Okay, so temperature is important for both solute solid solutes and gas solutes, but they're opposite. Gas solutes prefer a cooler temperature to increase solubility, where solids, for the most part, tend to prefer a higher temperature. Of course, not all of them. We'll look at a couple of graphs so you can see the visual of the solubility curves. And but trying to predict the temperature dependence of solubility is pretty difficult. You have to do that by experimentation. Okay, so here is some solid solutes being dissolved in water. Okay, so for the most part, you see the increasing line, but not everything works this way. So in general, though, overall, solids prefer a warmer temperature to dissolve more solute. And then our gases work oppositely. And so they prefer a cooler temperature. And that's why we store our Pepsis or our sodas in the fridge, because for one, it's better cold, and for two, it keeps it from going flat. Okay, now here's a interesting experiment that shows the idea that solutes can tend to have an effect on solvents' properties. So here we have some pure water, okay, and here we have an aqueous solution. Something is dissolved in the water. Okay, so what's happening is water is evaporating to try and reach equilibrium. So that's where the gas particles leaving equal the gas particles entering. Okay, so it's trying to reach equilibrium. But what happens now is the solute being in this solution is lowering the vapor pressure of this solution. So as more vapor ends up on top of it, the aqueous solution absorbs that vapor because it's trying to decrease the vapor pressure so that it can get back to equilibrium. So eventually, over time, all of that water will end up in this container, as you see in this visual. And it's all because the solute dissolved in this solution is lowering the vapor pressure. So the idea of trying to reach equilibrium and have equilibrium established. So that's how that works. Okay, here is just a little clip on the idea of equilibrium with vapor pressure.
At the boiling point of a pure liquid, a dynamic equilibrium is established between molecules in the liquid phase and molecules in the vapor phase. Some molecules at the surface of the liquid have enough energy to leave the surface and enter the vapor phase. Some molecules in the vapor phase collide with the surface. At equilibrium, the number of molecules leaving the surface is balanced by the number of vapor molecules that return to the liquid phase.
Okay, so that just gave you a quick overview of equilibrium. And remember, boiling is simply the balance when the atmospheric pressure on top of the liquid is equal to the vapor pressure of the liquid itself, then boiling can occur. Okay. All right. Now in this slide, it's showing the idea that when you add a solute to a solution or to a solvent, it affects the properties that the solvent had. And one of the things it does is it lowers the vapor pressure. And what that does then is that has an effect on boiling point and freezing point. And so that's kind of a practical application, and we call that a colligative property. And so I will let this play so you can see how this works.
The new liquid-solute interactions change the nature of the liquid phase. As a result, fewer molecules of liquid leave the surface to enter the vapor phase. The reduction in number of vapor molecules leads to a lower vapor pressure. A new dynamic equilibrium is established for the solution at a vapor pressure lower than that of the pure liquid.
Okay, so what that is saying is that now if this vapor pressure is lower than it used to be as a pure solvent, then that means we have to increase the temperature to get the vapor pressure up so that it equals the atmospheric pressure and a substance can boil. So that is called boiling point elevation. And the same thing holds true for something freezing. And so that's why we add antifreeze in our car's radiator so that in the summer the radiator won't boil over, and in the winter the radiator won't freeze. And so this is called a colligative property, and there are mathematical relationships with that, but because they're not on the AP exam, we are not going to look at those now. But the colligative properties that we may talk about just for a little bit and are involved when we make ice cream. So we'll bring that topic up when we go to make ice cream. So this is the end of the second podcast where we have discussed the energies associated with solution formation and then the factors that can affect solubility and how a solute-solvent interaction is adjusted when you dissolve a solute into a solvent. Okay.